Hello everyone. In the previous lecture, we studied about the registers, the shift registers, that is the serial in serial out shift register. In that, we also studied about the seesaw shift left operation, the seesaw shift right operation. We talk about the SIPO, that is serial in parallel shift register. We then studied about the EPO arrangement, that is the parallel in parallel out, and the PSO, that is parallel serial out shift register arrangement. So now, before starting the counter, just have a look on this topic of today, which is a ring counter and Johnson counter. So, my name is Shiv Charan Puri, Assistant Professor, EC Department, Assam Sugni College. So let's start ring counter. So what is ring counter? If the serial output Q0 of the shift register of the figure discussed is connected back to the serial input, we are now discussing, next slide, then an injected pulse will keep circulating. That means once a pulse is injected, okay, that pulse will basically circulate around the memories of the flip-flops. This type of arrangement, this circuit is referred to as a ring counter. The pulse is injected by entering 0001 in the parallel form after clearing the flip-flops. So suppose if it is a 5-bit flip-flop, then when the clock pulses are applied, this one circulates around the circuit. Okay. The waveform at the Q outputs are shown in the figure in the next slide. The outputs are sequential non-overlapping pulses, which are useful for control state counters, for stepper motors, which rotates in step, and that's why it is significant, because of non-overlapping pulses as such, which require sequential pulses to rotate it from one position to the next, etc. So as you can see here, this is the operation of the ring counter. As you can see here, okay, collection of flip-flop, as we have already discussed about the shift register. And you see here, this is again here. This last output terminal is again fetched as input to the first input terminal. Okay. So this is how the ring counter operates. So this is a 4-bit ring counter. So you can see here, this is a count sequence of a 4-bit ring counter. What happens when there is 0 clock pulse? Okay. When there is 0 clock pulse, there is basically only 1 and all zeros. Okay. When there is a first clock pulse, what will happen? This now, because as it was 0, now here it will be 0. So this 0 will be stored here, but as before here is 1 stored, this 1 will transfer to here, and it will be 0 1 0 0. Okay. Then you see here 0 1 0 0. Then it will be 0 0 1 0, and so on. Okay. And it will, you see here, this moves. This moves from one flip flop to another. This injected pulse, as we say. Okay. As you can see here, this is moving. So this is a state diagram of a 4-bit ring counter. Now let us discuss the timing diagram of a ring counter. So as you can see here, this is the clock. Now this is a Q0 output. Okay, this is the Q0 output. So as you can see here, with the first clock, this becomes 0. But as discussed in the first clock, this will transfer its input to here, so it will become 1. Okay, and then second clock pulse, now this become 1, and third clock pulse, this become 1, and so on. As you can see here, this is a non-overlapping pulses, as we said, and it is of immense use in digital electronics. The outputs are sequential non-overlapping pulses, which are useful to control state counters for stepper motor, which rotates in step, which requires sequential pulses to rotate it from one position to the next. So it is clearly illustrated from the timing diagram of the ring counter. Now let us assume that the flip-flop FF0 is initially set to a 1 and all other flip-flops are reset to 0. The counter output is therefore 1 0 0 0 for 4-bit operation. With the first clock pulse, this 1 gets shifted to the second flip-flop output and the counter output becomes 0 1 0 0. Similarly, in the second and third clock pulses, the counter output becomes 0 0 1 0 and 0 0 0 1. With the fourth clock pulse, the counter output will again become 1 0 0 0. Okay? Because we have connected the last output as input to the first flip-flop. So therefore, this 1 will basically rotate. Okay, and therefore it is called a ring counter. This sequence repeats after 4 clock pulses because it's a 4-bit operation in the present case. Now what is the advantage? An n-bit ring counter can count only n-bit, whereas an n-bit triple counter can count 2 n-bit. So the ring counter is uneconomical compared to a ripple counter. But a ring counter does not require decoder circuit because we can read the count by simply noting which flip-flop is set. That's the catch. It also has the advantage of being very fast. Since there is one pulse at the output of each of the n clock pulses, this circuit is referred as divided by n counter, or n is to 1 scalar. So next we will discuss about the Johnson counter. The Johnson counter, on the other hand, is constructed by providing feedback from the inverted output of the last flip-flop to the D input of the first flip-flop. So that means the structure remains same, just we have to connect from the complemented output of the last flip-flop to the input of the first flip-flop in case of this Johnson counter. The Q output of each stage is connected to the D input of the next stage, but the Q output of the last stage is connected to the D input of the first stage. Therefore, the name twisted ring counter. Okay. This type of feedback produces a unique sequence of state. Figure below shows the logic diagram of a basic 4-bit Johnson counter using D flip-flop. As you can see here, it is the same connection, just at the end, like in ring counter we were connecting it across here, but in Johnson counter we are connecting this path from the complemented output. Rest everything remains same. Now the question is, what is the impact? You see here, this is a count sequence of a 4-bit Johnson counter. Okay. So now this will move. This is a state diagram of a 4-bit Johnson counter. Okay. So Johnson counter is useful for the generation of multi-phase clock. Johnson counter is divided by 2n counter. For decoding the count, 2 input AND gates are required. So now let us discuss about the timing diagram. As you can see here, it requires 8 clock pulses. So therefore it is called, for 4-bit flip-flop. So therefore it is divided by 2n. Okay. Thank you.